For this solid shaft subjected to axial tensile forces as shown, let's imagine how it would deform. From experience, we know that it will not only elongate along the axial direction, but it will also contrast radially. It is impossible for this shaft to remain the original diameter. That will be against the conservation of material. The normal strain epsilon along the axial direction or the longitudinal direction is defined as the new length L prime minus the original length L divided by the original length, as we learned already. And the normal strain epsilon along the radial or lateral direction is defined as the new diameter d prime minus the original diameter d and divided by the original diameter. And the Puasson's ratio for this material nu is defined as negative epsilon lateral over epsilon longitudinal. Since in this case, epsilon longitudinal is positive and epsilon lateral is negative, therefore Puasson's ratio is positive. Similarly, if this shaft is subjected to axial compressive forces instead, it will contrast along the axial direction and expand along the radial direction. So in this case, epsilon longitudinal is negative and epsilon lateral is positive. Therefore, the Puasson's ratio is still positive. Just like density or Young's modulus, the Puasson's ratio is an important property of material. It is always positive, dimensionless, and is typically between 0 and 0.5. Just like the relation between normal stress and normal strain that we learned already, the relation between shear stress and shear strain can also be determined by experiments and represented by the conventional shear stress tau and shear strain gamma diagram, like this one. Just like the normal stress strain diagram, the shear stress strain diagram also has proportional limit, ultimate shear stress, and failure shear stress. And if you pay attention again to this linear region, this slope is known as the modulus of rigidity G, or shear modulus of elasticity. And within the proportional limit, the shear stress and shear strain is related by tau equals to G times gamma. Compare this to the Hooke's law, sigma equals to E times epsilon, and notice they have the same form. And just like Young's modulus, the modulus of rigidity G has the same unit as stress. The modulus of rigidity is also an important material property, just like Young's modulus E and Puasson's ratio nu, and these three are actually related by this equation, that G, the modulus of rigidity, equals to E, the Young's modulus, divided by 2 times 1 plus nu, the Puasson's ratio. So if you know any two of the three properties, you can calculate the third one. Let's look at this example. A cubic block with each side of original length of 4 inches sitting on the floor is being compressed by the force shown. If its sides along the x and y direction increased to 4.0001 inch, we need to determine nu, the Puasson's ratio, and G, the modulus of rigidity for the material. Assume it behaves elastically, and its Young's modulus E is 10 times 10 to the third power KSI. For this problem, first let's identify the axial direction. In this case, the z direction is the axial direction. Therefore, the x and y directions are both lateral directions, and according to the given information on the size change, epsilon lateral equals to the new dimension minus the old dimension divided by the old dimension. In this case, new sides 4.001 inch minus 4 divided by the original 4 inch, and that equals to 2.5 times 10 to the negative 5th power, and that is dimensionless. Don't forget both normal strain and shear strain are dimensionless. And along the longitudinal direction, the z direction, because material behaves elastically, therefore Hooke's law applies. Therefore, sigma z equals to Young's modulus multiplied by epsilon longitudinal. From here, epsilon longitudinal is calculated by sigma z, the normal stress, over the Young's modulus, and sigma z equals to force over area, P over A. Therefore, we substitute in the numbers. P, the force, is negative 10 kilopounds, negative because it's along the negative z direction. Area is 4 inch times 4 inch, and then Young's modulus 10 times 10 to the third power KSI, and then we can calculate epsilon, the normal strain along the longitudinal direction, equals to negative 6.25 times 10 to the negative fifth power. Negative sign indicates contrast along the z direction. And since we know both the lateral epsilon and the longitudinal epsilon, we can substitute them in to the equation to calculate Poisson's ratio nu equals to negative epsilon lateral over epsilon longitudinal. Notice how the negative sign get cancelled out, and that equals to a positive 0.4. And that answers the first part of the question, the Poisson's ratio for the material. Now, to determine G, the modulus of rigidity for this material, don't forget that modulus of rigidity and Young's modulus and Poisson's ratios, they are related through this equation. Therefore, substitute in Young's modulus and Poisson's ratio, we can calculate that G, the modulus of rigidity, equals to 3.57 times 10 to the third power KSI. It has the same unit as stress, just like Young's modulus. And that's the answer.